Hello everyone, thanks for joining today for the week 4 tutorial. I'm Kaustav Mukherjee, a PhD scholar at IISER Bhopal, and I'll start my screen sharing. Okay, so for today, I'm planning to take on some very interesting example of physics. So what we are going to do is, firstly, I'm going to do a light matter interaction. So this is similar to the NMR that you have seen in your lectures, but it involves a different kind of physics. So we are going to use the same two levels, and we are going to use light and see how an atom can be excited to state, and how to find the equation of motion in a similar way to your assignment question. And another thing that we are going to deal with is we are going to do some quantum circuits. So we are going to see how the if we use some kind of a rho in density operator, what we get out of these quantum circuits, how does it work. So we are going to do some examples of these quantum circuits today. Okay, so first I'll do with the light matter interaction. So what is a light matter interaction? Okay, so just a second. Yes. Now, so whenever, let's say you have an atom, and you obviously know that to excite an atom, let's say a hydrogen atom to some other excited state, you need a laser beam, right? Now, how does this actually work? So more or less the Hamiltonian, I can show you, write the Hamiltonian first, which we are going to try to derive, and then we are going to use uh, the equation of motion, like the time dependent Schrodinger equation, to find the equation of motion, which is similar to some of the question in your assignment. Okay, so the Hamiltonian precisely looks like, let's say these are two states, G and E. Then the Hamiltonian is something like this. Sigma EG. Okay, so this, if you write in the form of a matrix, it is essentially like this. So let's say the omega is a real quantity. For now, omega star equal to omega. Now this GE sigma is actually a density operator type thing. So it's a G bra G ket E. Oh, sorry, ket G bra E. Okay, so this is the definition of the sigma GE, and this is a similar Hamiltonian that you might have seen for NMR. So in NMR, you can actually write it in the form of sigma 2 omega by 2 sigma x. Now this omega is something that is called Rabi frequency. So we will see in this tutorial how this Rabi frequency is obtained and what does it actually signify in your real system. So when you have an atom and you have a laser interacting with that atom, then there are a lot of things, like it's not just about the electron getting excited. So why I am doing this is, it's showing the beauty of physics, that some Hamiltonian that you have seen in some other context can be used in other different areas of physics as well. Just like the angular quantum numbers, the eigenvalues that you had obtained can actually be used for spin quantum numbers as well. So there is a symmetry in physics. So in different areas of physics, you can actually understand using the same kind of concepts. Okay. Now to understand this, so you have seen in NMR that professor has talked about something like you use B cos omega t, something like that, to introduce the field. Sorry, yes. So here also we are going to use a similar kind of a perspective. So we are going to use a electric field here. Okay, and the electric field, so we take a vector potential in the form a naught epsilon cos k dot r minus omega naught t. Okay, so here omega naught is basically your laser frequency, and this is your wave number. K is your wave number, that is 2 pi by lambda, that you already know. and epsilon is your some constant, let us say. Okay, and a naught is obviously your amplitude. Now you know how to derive a electric field from a vector potential, right? So what you do is, like from Maxwell equation also, you can see that you can find the electric field from the derivative, time derivative. So this essentially gives us what? A naught epsilon omega naught and your sign with the minus sign here. Okay, so this is essentially your E naught, that is the amplitude of your electric field. Okay, so let us see how one can derive such Hamiltonian. So this is something like a very simpler Hamiltonian that you have already seen in a NMR context as well. So if you consider such a complex vector potential, then there are some approximation that you have to consider in order to derive such simpler Hamiltonian, and then we are going to find out the equation of motion. That is how, let's say for a very standard psi, you take a wave function that is Cg g and Ce e. So to find out how this Cg and Ce evolves, time evolution of this coefficient, we are going to use the time dependent Schrodinger equation. Okay, now before that, let us simplify the Hamiltonian first. Okay, so now there are two terms. So this laser is actually couples these atom to a ground state to an excited state. Okay, so that means it can't be on the diagonal of the Hamiltonian. So these mainly lie on the off diagonal terms, because these are what we call as coupling terms. Okay, and the diagonal ones are essentially what someone usually expresses as a site energy. Okay, so let's say the energy can be shifted to a 0 point energy, and you can neglect them out. So you can just put them 0 whenever, if you feel like there is, let's say, EA and EB, you can actually difference them out and such that the diagonal elements are 0. Or if, let's say, EB is not equal to EA and there is some finite, what we call as a detuning. A detuning means that the laser is not in resonance with the coupling frequency. So let's say the difference between the energy, so you know that the laser frequency you will need is given by in this form, right? The energy difference between the two states. Now if you don't have a laser with this particular frequency, let's say you have omega naught, which is not exactly this, but some delta away from the main resonance frequency, and in that case what we call this as a detuning, and we will see how this detuning actually affects the excitation of such system. Okay, so in order to find the off diagonal terms of the Hamiltonian and reduce it in a simpler form, you can use, so let's say we have phi e h phi g. So this is an off diagonal term because the states are different, and we are going to find this term. Okay, now this is, let's say, some constant. So here we had, sorry about this, so these were some, let's say, constants are there. Okay, so we essentially need from the electric field a constant times phi b. We had cos omega t, so there is k dot r minus cos omega t. Phi a. So this is like any general electric field that you can consider. Okay, so all kind of like mostly planar waves or any electric field that you generate are in the same form. So this is like a generalized expression that we are trying to derive here. Okay, Now, so first approximation that one takes here, so cost can be written in the form of exponentials. So sorry, omega naught was there, which is the laser frequency, and we have phi a on the other side. Now the first approximation that one consider is something called a dipole approximation. Now what does this mean is that the k dot r, so this exponential of k dot r is essentially taken to be as 1. Now what does that mean is that this is a very fast, let's say your lambda is very higher than your r, so this gives rise to a enormously huge number. Okay, and an exponential to the power ikr actually is represented in a phase plane with a pointer. So if the number is too high, it actually rotates a lot and gives out a 0. Okay, so firstly we use a dipole approximation. So this, what does that do is essentially put these terms to 0, and we only are left with the omega naught terms. Okay, so okay, let me rewrite it. So we had phi b h phi a. So you can actually rederive it in your way to find out all the actual constants as well. I'm just doing a rough overview of how you obtain such type of a simpler Hamiltonian. Okay, now what you are left with here is phi b e to the power minus I omega naught t plus e to the power t phi a, and yes, okay, right. So, and we also had an epsilon. So this is what your dipole term comes from. So when you, and there is a Laplacian as well, right? So from here actually you can write in the form, so we keep these constants as k, and let's say we take these out. Okay, you take these e to the power minus I omega naught t plus e to the power I omega t, and we had some other terms in the expression that I have missed, and when you use those terms, so sorry about this, so these were supposed to be inside here, and these term actually gives us something called a omega, which is essentially depends on the laser intensity. Okay, so this comes from your transition dipole matrix elements. If you want the full expression, then I can show you later on if you want it, but for now, just for a rough overview, you can use this to understand. Okay, now usually how we get these time dependent coefficients, right? So from the Schrodinger equation, you do h of psi. So this is what you call as a time dependent Schrodinger equation that you are already very familiar with, right? Now if the energies are constants, okay, so a general time dependent wave function is usually written in the form minus t by h bar for, so this is g plus ce h bar. So where Eg are the energy of the level. Okay, so Eg is your ground state energy and Ee is your excited state. So if you don't have any other coupling, let's say you have a very simple Hamiltonian where you have two levels with two different energies, then this is what you get as your time dependent wave function, right? But now when you have extra levels that you have to consider, not extra levels, I mean extra couplings. So you are introducing a laser. In this case, there is no laser here. And when you introduce this laser, so now you can actually write in the form of this way. So you have same, let's say we write in the matrix form. So it's psi, and we have your extra couplings. So let's say we write in Cg dot Ce dot. This is a time derivative of the coefficients. And let's say we only have the off diagonal now. So we have already done for the diagonal ones. So any Hamiltonian can be written in the form of this. So you can separately do the calculation for each of the part of the Hamiltonian, right? So here we have this part. Now so we are going to use this into the expression here. So what we are essentially going to get is something, so HAB that we have derived is in the form of I h bar. Let's say there are coefficients, so this was written as K, right? And we had an e to the power I omega naught t plus e to the power I omega naught t. Now when you put these terms with these expressions, right? So sorry about this is malfunctioning a bit. So if you actually take this, let's say, coefficient out, or not the coefficient, you take the exponential out, so you can actually write it in the form Ce and this is nothing but your frequency between the two states, right? So there is one more approximation that has been used, that is something called rotating wave approximation, in which the similar concept is used. So whenever you have omega naught plus omega GE, then this term becomes large and you essentially neglect that term. And whenever you have omega naught minus omega GE, sorry, which is essentially your detuning, that is the delta, right? Then you keep only those terms, okay? And finally, when you put this here, you get something of this sort. After ignoring all the terms that has a very high frequency, you are only left with the ones that have this detuning part. Now this is still not a very easy or elegant way to solve, right? Because you can see that there are complex exponentials. So in order to reduce this term further, what you can do is you can use some tricks, like you can take this CG or let's say the CE to be a substitution method, something like that sort. So you can use this as a substitution. Let's say we call it CE tilde. Okay, now when you use this as a substitution, so as maybe something's wrong with it. Yes. So when you use this as substitution, you can take the derivative of CE tilde. So what you will find is your I delta will come down. So you will get I square delta CE, and next you will do the derivative of CE, which is your normal CE dot. Okay. Sorry about this. Right. Similarly, you just keep your CG to be same, so you don't really do any substitution for CG. You keep, but since we are using the tilde form, so we are going to substitute all of them into the tilde form. Right. Now, if you substitute your CE dot from here into this, what you will get, so your CE dot essentially is written in the form minus I h bar omega naught t. So if you have any questions at any point of time, just ask me. Okay, and okay. So when you substitute your CE dot, so here you have I h bar, it's cancelled out. So just pardon me for the coefficients, there can be many I h bars and all. I might get confused at times, and you can point out if there are any mistakes. Okay, so we have delta CE, and we substitute minus omega 2 delta t CG. Right. So this part gets cancelled out, and we have left with CG, and we know that your CG is essentially CG tilde, so you can directly substitute, but we have to resubstitute, that is we have to go the opposite way. So your CE can be written as minus I e to the power I delta t CE tilde. So we are going to write all the terms in the form of tildes. So this essentially comes in the form minus I e to the power delta t CE tilde I omega 2 CG tilde. Now this part gets cancelled out too, so we are essentially remained with minus I omega by 2 CG tilde plus delta CE tilde. And if you write your I CE tilde here, so this essentially reduced down to right. And for CG, the expression was direct, so we had I, so this had a dot, I h bar CG dot, so you can also put your h bars, is essentially your I h bar omega. I can actually copy paste. So okay, that is not working. Okay, I'll just write down I h bar omega e to the power I delta t CE. Just checking once, minus I, right? And CE we have just seen here that it is written in the form minus I e to the power I delta t CE tilde. So minus I e to the power I delta t CE tilde. So this again gets cancelled out and we are left with minus, okay, I gets squared, so we don't have a minus, we have h bar omega by 2 CE tilde. So if you just like for the moment ignore all the h bars, you have in the simplest expression you have your dots given in the form 0 omega by 2 and delta. And you know, for this part the Hamiltonian is very straightforward. You just write in the form omega by 2 your GE plus omega by 2 EG, and delta is the detuning to the excited state. So this is a straightforward Hamiltonian now you get from the expression. Okay, and in order to find the equation of motion, so let's say we solve this. Okay, so let's say we solve for detuning equal to 0. So this is again gets even more simpler. So you have your CG tilde as omega by 2 CE tilde, and you have your CE tilde as omega by 2 CG tilde. There are dots. So this is basically your coupled differential equation. Okay, so what you do is you take the double derivative of CG, and what you get on the right is a single derivative of CE, and you basically substitute this here. So what you will get is minus I by 2 CG. So your I gets cancelled out. So essentially this might look very familiar to you, as this is nothing but your harmonic oscillator type equation. There is a minus sign. So you must have seen something like this, minus sorry, not omega square x, right? So this is very similar to this one, and you know already the solutions are in the form of a cos omega by 2 t p sine omega by 2t. And similarly for CE you can find a similar type of an expression of, let's say, C cos and sine. Now to find out the exact values, what one would do is, let's say you are initially in the ground state, that means your CG at 0 is 1 and your CE at 0 is 0. So you can use this grounds boundary conditions to find out the exact expression how this CG of t actually follows. Now to understand this, so what this Rabi frequency actually means, that is your excitation. So when you are your atom is driven by a laser, so let's say this is CE initially and you had CG as 0. So let me use different colors. So what happened is, what your CE will oscillate and go down to 0 and then again go back up, while your CG from 0 goes back to 1, and this type of oscillations take place. Okay, so what we call this as your Rabi oscillations between the two states. Now let's say in an experiment you want the system to be in a completely excited state. So what you do is you shine the laser only till this part and you stop it. This is, I think, called a pi pulse. Okay, so what it has done is that it has excited with a complete probability. So when you stop the pulse right at this point of time, then you are certain that your state, your atom is in the excited state. Whereas if, let's say, you stop the laser at this point, which is, I believe, pi by 2, it can be pi and 2 pi also, or pi by 2 and pi by 4. So let's say it's pi and pi by 2. Okay, sorry, something happened. Just a second. My screen. Okay, it's not working. Just give me a second. I'll share it again. Okay, yeah, it's back on. Okay, right. So what was I saying? So if you okay, something is going wrong. This thing. Okay, it's not working. Okay. So if you shine a pi by 2 pulse, then your system is actually in a superposition state. So it is actually having a G and E. So in order to introduce a superposition state where you have a 50% probability of being in the ground state as well as 50% probability of being in the excited state. So this is what we call as a quantum superposition, right? So you can use this laser to create different things, like you can excite, you can create a superposition, or you can do a different kind of things. And this Rabi oscillation means this oscillation that I'm showing here. So this is oscillating with the frequency omega, which we were using before, and this omega essentially depends on your laser intensity. So higher your intensity of the laser is, the faster will these Rabi oscillations be, and slower, the lower laser intensity means there will be less Rabi oscillations, right? So, and what happens if you have a high detuning? Let's say your detuning is not equal to 0 and you have a very high detuning, and in that case what essentially happens is that your laser is not completely resonantly coupling the two states of your atom. And in that case, what one usually sees is that, so if you are initially in the ground state and your excited state population is 0, then this essentially oscillates with this form. And this difference actually increases as you increase the detuning. So a very high detuning means that your ground state remains the ground, and the atom does not get excited to the upper level at all. Okay, so the probability of getting excited decreases. So as you increase the detuning, this peak will keep on decreasing and decreasing, and there will be a point of time when you have no excitation at all. So there won't be any probability of getting excited at all. Okay, so this was the light matter interaction, how a light and atom interacts. Now we will switch on to the theme that was used in this week's lectures, that were your quantum computing. So let us do a short recap on the gates that we had seen, and we will solve or see some quantum circuits and how to find the density matrix of a quantum circuit, and also the unitary operator that one can use. Okay, so first of all, I'll just give a short recap on the gates. So first of all, we had a Hadamard gate, which essentially creates a superposition state. So if you operate a Hadamard gate on 0, you get a 0 plus 1 superposition. If you operate a Hadamard on 1, so here we have two states, qubits. So previously we had G and E state. These are replaced by 0 and 1. It's the same concept here, nothing different. So you can use it as any name you want. You can use up and down or anything else as well. So let's say we are, since it's quantum computing, we are going to use qubits. So we are going to use the 0 and 1 notation. Now when a Hadamard operates on 1, you get superposition but with a minus sign. Similarly, you must have seen in the lectures that there are sigma x gate, sigma y gate, sigma z gate. So essentially your sigma x is written as your 0 1 1 0. Let's say these two are the most few of the most important gates. So sigma z is 1 0 0 minus 1. Now what does that do? So sigma x essentially is a NOT gate in your classical sense. So this gives you 1 for 0 and 0 for 1, whereas sigma z gives you the same for 0, whereas it just flips the sign to minus. Okay, so and there is one again a crucial gate, that is the C0 gate. Now C0 is a 2 qubit gate, so there is one control qubit and one in which the control thing happens. Okay, so let's say this is psi 1 and psi 2. Now what C0 does is, if this control bit is 0, then it does nothing, but if it's 1, then flip the bit like sigma x. So for example, if you are operating C0 on 0, let's say 1, then it won't do anything and you will get the same state out. But if it's operating on 1 1, then it will flip the bit, so you will get 1 0 here. Okay, so let us try do some questions and see how it actually works out. So firstly we have a circuit in the form. So these two are the Hadamard gates operating on both. So we have a row input. This is your first qubit, this is your second qubit, and we are to find row out for a given row input. So let's say your row input is something the sort. It's a entangled superposition, and we have to find your row out from this row in. So let us see what each gate does to it. So in general, one usually write in the form C0 to H. So you can write as you want. So these H are operating simultaneously. You can write H1, H2 on your row in. So these subscripts, so this can be my notation as well. I'm not sure what others use. So this subscript mean the qubit it is operating on or acting on. Okay, now so let us see. Okay, something's wrong. Right. So let us first operate the Hadamard gates. Okay. So let's say you're operating your H2 first on the row input. So what it will do, it will only act on the second qubit of the 2. Okay, so that is this qubit. So how will it do it is, so your first qubit remains the same, and it creates superposition for the second qubit, and similarly for the second part -1. So now if you write the whole thing, you get, let's say we take the 2's out. 2, there is a 0 0 0 1 1 0 and -1 1. Now your Hadamard 1 is operating, so this is, so we already have the row, let's say we call it row 1, so h1 row 1. So what this essentially means is that your h1 is acting on 1 by 2 0 0 so this will act only on the first qubit here, right? All the first qubits. So this might get a bit longer. So what you will have, your first qubit becomes a superposition, the second remains the same, similarly here, zero -1, since this is 1 0. So actually you can write, taking this as, you can also take this as common since they have both 1, and you can write as 0 -1. Okay, now again taking the root 2's out, you have 1 by 2 root 2. There are a lot number of states now, so you have 0 0, you can actually add them up later, 0 1 1 1 plus 0 0 minus 0 1 1 0 plus 1 1. So here you can see that there are some states that are actually cancelling out, so that simplifies a bit, and some states are doubled up, so you essentially get your 0 0 plus 1 1, which was your initial state itself. Now next part, you have to operate C0 gate onto this. Okay, let me just check. So if you spot any mistake at any point of time, just let me know. Okay. Okay. Now operating your C0 onto h1 row in. So let's say this is your row 2. Now, so you're operating C0 on row 2, and what you get is your 0 0 plus 1 1. So whenever the first control bit is 0, it doesn't do anything, and when the first control bit is 1, it flips the other bit. So it essentially keeps the 0 0 as it is and flips the other bit as your 1 0. So this is what you can say is your row output. Okay, now what if you are supposed to find the unitary matrix for this? So that means your row out is essentially u row in, and this is the unitary transformation matrix, or that the whole circuit is encapsulated in. So this U defines your whole quantum circuit here. Okay, now in order to find this, what you have to do is you have to find each of the elements, that is 0 0 0 1 1 0 1 1, and in order to find that, what you have to do is you see how what exact operations that you are doing on it that impacts the result. So let's say you find out your U00 through your operations. C naught 2, then you had H2. Yes, Ramya, you had a question. Okay, fine. And then you have your H1 H2 operating on 0 0. Okay, so this is straightforward, you have actually done it previously. So I'll just do for one, you can do for all the others. So let's say H1, so H2 operating on the second qubit gives you 1 by root 2 0 plus 1. Now H1 operating on the first qubit, so you can write from here itself. Okay, so there is an extra root 2 here. So you will get a 1 by root 2 again from that one. Now writing the whole part, you have 0 0 0 1 1 0 plus 1 1, and now you know what the C naught gate does here. Okay, it's again not working. So your C naught gate essentially changes only the ones, only the one with the 1 in the first qubit. So it actually doesn't change the state at all here. So this part get to 0, this part became 1, and what you are getting here is what was already there previously, and this is your U00. Okay, so based on this you can actually find the first column of your 4 by 4 matrix. So all the elements are 1 here. Okay, and you can similarly find all the other elements through operating on 0 1. This will give you your second row, and 1 0 your third row, and finally your fourth row comes from the U11. Okay, now let's take a more complex setting. So let's do a 3 qubit state. Okay, a 3 qubit sorry, I don't understand. Ashwini, do you have any question? Okay, maybe that's a mistake. Okay, so let's do for a 3 qubit, and we have a circuit, the form. Let me just make the circuit. Yeah, it's fine. So now this contains a double C naught gate. So let me briefly tell what does that mean. Okay, so we have a row in and a row out. Now double C naught gate usually means like the both have to agree to make it flip. So whenever these two are 1, only then this bit flips. If any of them is 0, then it does not work. So if you have 0 0 0 1 1 0, it doesn't do anything, but when it's 1 1, it flips. It's similar to I believe NAND gate in the classical uh, analog theory. Okay, so this is your CNOT gate acting on 3 qubits. So let us again take a very, let's say, entangled state. So we have 0 0 0 plus 1 1 1. Okay, and we operate one by one onto these. So let's say we operate h. So as the time flows through this side, we are going to operate each by each. Okay, so finally we have total operation, something looks like this, and h1 c0 on 3, sigma x on 2, h1 on rho n. Okay, and this is the rho n that we are considering. So firstly, operating your h1 on rho n, let's see what that gives us. Okay, so it mainly operates on the first qubit only, right? So what you have here is 0 becomes a superposition. You have all the other zeros. Similarly, the 1 becomes a superposition, and you have the other ones as it is. So what you get in the end is 0 0 1 0 0 0 1 1 and minus 1 1 1. So you can see this is a highly superposition state. So we started with a simple entangled state, and now we have increased the superposition by a simple Hadamard gate. Okay, now once you have this state, let's say this is your rho 1, next up is we have to operate a C0 3 on this rho 1. So that means whenever 2 qubits are 1, then only the third qubit is flipped, right? So from this you can see that only this part will only matter. So let us see that in actual sense. So we have 1 by 2, 0 0 0 0 0 0 1 1 minus 1 1. So for the first qubit, you can see both are zeros, it doesn't do anything, so we have it as it is. For the second qubit, we have 1 for the first one but 0 on the second one. That means again it won't do anything at all, and we end up with the same state. Similarly, for the third one, we have 0 and 1. Again, it does not agree, but in the third one we have 1 1, so that means your state becomes 1 1 0. So this is, let's say, your rho 2 after your C0 operation from your of the previous state. So Hadamard on rho 1, rho in, then we had C0 3 on rho 1, and finally we have to use sigma x on rho 2. So sigma x2 means it is acting only on the, so you can see it's only on the second qubit, your first, second, third qubit. So Hadamard on first, C0 on third, and sigma x on the second qubit. And what does sigma x does is just flips the qubit. So let us say okay, so we had sigma x2, one zero zero minus 1 1 0, right? So it's only operating on the second qubit. That means only these will be flipped. So there are no conditions here, it has to flip. Okay, so that means you get your states as 1 0 0 0 1 and minus 1 0 0. So this is what you can say your row output is. Please interrupt me whenever you have any questions. I hope these are clear. And for to find the unitary operator for this, the matrix U, again you use a very similar way. Okay, so let's say, so the dimension you can obviously guess from here that it is going to be a pretty large matrix of possibly 9 by 9, I think. 2 4 2 3 8. Okay, so there are 3 qubits, that means the dimension is 2 to the power 3, that is 8. So it will be a 8 cross 8 matrix. Okay, so there are 8 possible ways you can write, right? So you have 0 0 0, your 0 0 1, 0 1 0, 0 1 1. These are 4, and then again there are other 4s, 1 0 1, 1 1 0, and 1 1 1. So all these 8 qubits, so your 8 rows and 8 columns. Okay, so let us see what does your U on 0 0 0 does, and rest you can yourself do to find out this U matrix, which is your basically the quantum circuit. So what we had here was your sigma x on 2. This is just doing it all over again. Actually, let's take a qubit which was not present in your row n. So we had 0 0 0 and 1 1 1. So let's take a random one. Let's take this row 1 1. So this will give you our fourth row. Okay, so you have C naught on 3, H Hadamard on 1, and acting on 0 1 1. Right, so this probably now looks straightforward from here. So H1 is acting only on the first qubit, so I'll just write it directly, 0 plus 1, tensor product with your 1 1. Right, now your C naught 3 is acting on wait, I'll just write down the state first. So your C naught 3 is going to act on which one? Can anyone tell? It's pretty straightforward. So the ones in which the first 2 qubits are the control ones. So you obviously know that since these two are the qubits where there's 1, that means only this bit is going to get flipped, right? So I believe the quantum computation is probably now getting straightforward. So you can easily do all kind of computations and all kind of quantum circuits you can create, and to do different kind of problems. You can solve many kind of problems using these quantum circuits. So implementing or acting the C naught 3 on the third qubit, so that gives us your 0 1 1 plus 1 1 0. And finally you have your sigma x2, which only acts on your second qubit, which are these two. So what that gives us is your 0 0 1 plus 1 0 0. So this was U acting on 0 1 1, and similarly you can do for all other 7 states, and you can find your final U matrix for this case. Now finally I'll take one simple example which has a different gate. Okay, so let's take again a 2 qubit example. So we have already done a 2 qubit, so it is pretty straightforward by now. So let's say we have an additional different gate here. So we are using sigma x and sigma y, plus there is a swap gate. So I probably have not yet told about the swap gate. So what does swap gate does is, Okay, so if you have a state, okay, just give me a second. This, yeah, if you have a state A, B, then a swap gate essentially makes it BA. It just interchanges the bits. Okay, so let us do it one by one. So we have uh, swap, then let's say sigma y1, sorry, sigma y on 2, sigma x on 1 for the row in, and we use the same row in that we have used previously, and let's see how it operates on it. Okay, so we have to find the row out. Something's wrong with this thing. And this is your row out. So let's first take sigma x1 on your row in. So sigma x1 will only operate on the first qubit, and it essentially just flips it. Okay, it just flips the bit to 1 0 plus 0 1. Okay, now sigma y, you probably know it's given in this form. There can be minus sign here and there, sorry about that. So let's just quickly solve it out. So sigma y2 operating on your, let's say this is your row 1. So we have what it does is it flips, and it also has the I along with it, right? So let me just check one. Sigma y is, so when you put, I'll just write down here for reference, you get 1. Sigma y on acting on 1 gives you minus I 0. Okay, so yeah, the signs are right. Okay, so we have your row 1 here. So sigma y2 acting on 1 by root 2, 1 0 plus 0 1. So this, so from based on these you can easily see that it's just a sigma x with an additional I. Okay, so what does that gives us? So it's acting on the second qubit, so sigma 0 gives us a I, so we have I 1 1, and acting on 1 gives you a minus I 0 0. So this is nothing but your I by root 2. Let's say take the minus n out, 0 0 minus 1 1. And finally the swap gate. So you can straightforward see that both qubits are actually the same here. So that means the swap gate won't really do anything at all. So when you put the swap gate on row 2, it just, since it's swapping the 2, it doesn't do anything special here, and you get these state. So your final row out is nothing but 0 0 minus 1. So this is your output density matrix, and similarly you can find your sorry, this is not really density matrix, sorry about that. These are the states. This is psi out, not row out. I'm so sorry about this. Okay, these are all psis. Okay, and you can similarly find out your u here. Okay, so I'll just stop this class here. If you have any question, you can just ask, and I'm sorry about the rows and psi mixed up. Okay, so if you don't have any questions, so thank you all for coming for this tutorial. So good evening, bye bye.